Hello, welcome to your lesson on higher order derivatives. Let's begin with some mental math. So no paper, no pencil, only your brain. Okay, just in your head, what is the first derivative of this function? Okay, and now, what is the second derivative? What is the second derivative? Well, you've taken the first derivative. Now take a derivative of the derivative. That's the second derivative. So what is it? Okay, still no paper and pencil. Continue on. You have the first derivative, you have the second. Now take a derivative again. The third derivative. What is it? Okay, I hope you did all that without paper and pencil, and hopefully it went okay. Here are the answers. We have our original function, first derivative by power rule, drop all the powers, lower them by 1. Second derivative, right here, is shown like this. Notice that 3 dropped down, we're down to here now. And then third derivative, look, f triple primed looks like this. So that's all that higher order derivatives are. Okay, let's try one more. This one's gonna be a little tougher. Still, only your brain, no paper and pencil. What is the first derivative of this? Okay, and now what is its second derivative? This is tricky. You're tempted to grab a paper and pencil, I know you are, but let's check. So here's our first derivative. We dropped the 5/2 down, multiplied by 6 became this. That can simplify to this. And then you're thinking of that. Second derivative, drop the exponent again. You get this lowers by 1, there we go. Hopefully you were able to do that. If not, that's okay. That one's a little tricky, but it was just a good test of your mental powers. So those are higher order derivatives. You can go forever. Let's go to the next one here. So higher order derivatives. Let's say we begin with the function f of x. The first derivative, we know we write it as f primed of x. Or dy dx, that's the other notation, right? Delta y over delta x, change in y over change in x. Again, that brings us back to the definition of a derivative, where the derivative is a slope at a moment in time. Second derivative would be f double primed of x, or d squared y dx squared. Okay, that's kind of strange that we have those squares, but that's just the notation for that. And third derivative then will be f triple primed of x, or d cubed of y d delta x cubed. Okay, there we have it. So here's some examples. Find the first two derivatives of this function. Nice easy one to start. Let's do it. Great, check your work right there. First derivative and second derivative. How about this one here? Given this function, find f double primed of 1. So now you're finding the second derivative and then putting 1 into it. So you're finding the slope at the x equals 1 on the second derivative. Okay, so check your work. Here's the function, here's the first derivative, here's the second derivative. Here it is simplified with that move to the denominator, and then the 1 has been substituted in to get you that number. Check your work carefully. All right, example 3. Here we have a function that is not using y or f of x, different notation, but still a function, s of t. And here you notice the independent variable is t. Okay, so it's asking you to find this. Remember, don't be confused by this. This doesn't mean you have to find something and square it and do all these things. No, this just means find the second derivative. Second derivative of s in relation to t, right? So this is always like your y thing, and this is your x thing, right? So s and t. So it's just the same as writing dy dx, but we have s and t here. Okay, so find the second derivative. Check your work. First derivative, ds dt. And then second derivative, right here. Example 4. This time we're given this, and we need to find this. Try it out. Okay, I hope you weren't tricked by this one. This one gives you the first derivative already. So if you were looking at this and thinking, okay, I gotta take the derivative of this once and another time, nope, you only have to do it once because you're already given the first derivative. So to get from the first to the second, you only have to take the derivative once, and that's what we're doing here. Okay, let's try another one. So look at this question. You're given this function, and then it says find the value of x for which the second derivative equals 0. So find the second derivative, set it equal to 0, and solve for x. You're going to use the quotient rule. And using the quotient rule, notice we here, when it shows the answer, it actually found u prime, v, and v prime. So it kind of found the four pieces so that when you have the quotient rule, you have the four pieces you need, you put them in, and you get this. So that was your first derivative. And now it's quotient rule again. So if you love quotient rule, this is your favorite problem. You've done quotient rule once, and now you're going to do quotient rule again. So here it is for the second derivative, doing quotient rule on this one. Here's all that work. Check your work carefully. Lots of simplifying there. Gets us to a certain point. But in the end, it says set the second derivative equal to 0. So that's what we're doing here. If you set all of this equal to 0, this x squared plus 2 to the fourth power will cancel, and then you'll have three factors, each of which can individually be set equal to 0, and solve. And when you solve each of those three factors, you get two possible solutions right here. Great. This one is definitely the toughest of the bunch so far, so you might want to pause and check all your algebra carefully here. Okay, let's take a step forward from that. When we talk about derivatives, we also are going to be talking about the graphs of derivatives. Of course, we have an original function that you can graph, but then also you can graph the derivative, and you can graph the second derivative. And there's relationships between all these graphs that we're going to look at now. So let's talk about graphing derivative functions. And let's begin with this opening problem. Here, you are given the graph of a derivative. See, notice this is f primed of x. So this is not the original function. This is a graph of a derivative of some function. And then it says write down the intervals on which f, which is the original function, is decreasing and increasing. So think about that carefully. If you're given a derivative, does it tell you where the original is increasing or decreasing? Let's see if you can answer this. Okay, this is tricky, so let's think very carefully about this. Remember, the derivative function represents the slope of the original. So over here, all these positive values of the derivative function are telling us that for these x values, the slope of the original is positive. And that's true over here as well. Here we have positive values of the derivative, therefore the slope of the original must be positive. So when the derivative is positive, and it's positive here and here, that tells us the original is increasing there because it has a positive slope. Now look down here. Down here, the derivative has negative values. These are all negative y values. So the derivative is negative down there. And that's when the derivative is negative here, that tells us the original is decreasing for those x values, because a negative derivative tells us there's a negative slope. So therefore, from here to here, the graph has a negative slope. Okay, so that means the original graph is increasing here from negative infinity in terms of x values all the way to negative 2 on the x values. And then the derivative becomes negative after, the derivative takes on negative values after an x value of negative 2. So here, the graph must be decreasing. So f of x is decreasing between negative 2 and 4 because derivative values are negative between negative 2 and 4. So that means there's a negative slope on the original graph between negative 2 and 4. So it's decreasing. And then again, the derivative becomes positive here. And that means now slope values on the original graph are positive, so the original graph must be increasing greater than 4, x values greater than 4. So here's that. This is a tough concept to grasp at first, so just take a look at everything that's written here, pause, and just really ponder again. What does derivative represent? Represents slope. So these values are telling us what's going on with the slope of the original, and then take a look at this again, make some sense of that. Okay, let's go online and see something that's going to help support this concept for us. So let me find it. Over here is the first thing. Okay, so here I'm going to have, here's a normal parabola. Let's say that's our original graph. And that parabola has an equation y equals x squared. So the derivative of that is 2x, right? Let's put that graph, so again, derivative of that. So I'm going to put the graph of the derivative. There's the graph of the derivative. Let's talk about what we have here. Look at the original graph, the red one. it has a negative slope, negative slope, negative, 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 until we get to the vertex, and then there's no slope. And remember, derivative graph represents the slope. So if this is all negative slope, look at the derivative graph. It's all negative y values here, negative, 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 but the negative values are getting smaller. And that's saying that this slope is becoming less of a negative slope. And we can see that it's very steep, and then it's less steep, less steep, even less steep. So there's just a little bit of negative slope here, and that's what this represents, a little bit of negative slope. And then this is going up, and look, the blue line hits here. It says there's no slope there, and we know in the original graph there is no slope at that point. But after that point, following the red graph, the slope is positive, right? The slope is positive, but it's a small positive slope first, and then a bigger, bigger, bigger positive slope. And that's what we see on the derivative graph. It's a small positive value. We're talking about y values. Small, small, bigger, growing, growing, bigger, bigger, bigger positive y values because the slope is becoming bigger. So negative slope, no slope, positive slope, and that's what we see on the derivative graph. Negative values, no slope, 0, positive values. Now let's take the second derivative. The derivative of 2 to the x is just 2. So now I'm going to put that in here. Let's graph that one. Look, it's a horizontal line. Y equals 2. Why? This one represents the slope of this one, right? Just like the blue one was the slope of the original, the green one is now the slope of the blue one. And look at the blue one. The blue one is a line. It has a constant slope, and that slope is 2. We can see rise 2 over 1, rise 2 over 1. And so this green one represents the slope of the blue one, and it is always 2. Okay, let's look at that in the reverse situation where we have a negative parabola. Now when you have a negative parabola, like this, concave down, it begins with a positive slope, no slope, and then negative slope. So let's look at that on the derivative. The derivative of negative x squared is negative 2x. Here's that graph. Okay, again, this had a positive slope, no slope, and then negative slope. Look, positive values becoming smaller, no slope, 0, and then negative values, therefore negative slope. So we can see, again, it matches the graph. The blue one shows us what's happening with the slope of the red one. And then the derivative of this is negative 2. So there's negative 2. And again, the green one is the derivative of the blue one, or it's the second derivative of the first one, but it's the derivative of the blue one, so it's telling us about the slope of the blue one. And the blue one has a constant negative slope of negative 2, therefore we have negative 2 here for that one. Tough stuff. We can talk more when we see each other about this as well, but ponder that for a bit. Let's go back. Okay, a couple more things we're going to do together. So here we have this. Now I would suggest you put a blank piece of white paper on the screen, and your job or your challenge is, this is an original function, and I want you to draw what would the first derivative function look like and what would the second derivative function look like. Now, a couple tips to get you started. First of all, the places you should always begin are, where does this one have no slope? And we know it has no slope here. So that means when you graph the derivative will have a value of 0 at this place. So the derivative will have to hit the axis here, because this is no slope, and this place represents no y value of 0, no slope. Is there another place where there's no slope on the red one? Yep, when I get to here, there's no slope. So that means on the derivative graph, it will have to be right here at that moment, because it will have no slope, a value of 0 right there. So next step is to say, okay, this graph has a positive slope until it gets to here. So positive slope. That means when you graph the derivative one, it's going to have positive values until you get to this point. So think about what that's going to look like. And then here's negative slope. So the derivative graph will have to have negative values after this point. Okay, what does it look like? So try to draw both the first and second derivative. Okay, here's what it looks like. So here's this one. See, look at this. Positive slope, but it's a decreasing positive slope. So here's positive values until here, no slope, gets to 0. And then negative slope, but then growing slope, getting to 0 again, no slope. So negative, but becoming less negative, getting to 0. And then positive slope, blue line going here. And look at the green one. The green one represents the slope of the blue one. The blue one has negative slope, so negative slope until you get to here. All right, until you get to here. And then it has an increasing, then it has positive slope. So look, no slope, and then positive slope here.